maybe on leadership.
So, one of the burning questions that I'd love you to kind of put in your head and marinate throughout this next project is when you think about STEM and you think about science and mathematics and engineering and technology and how these things all relate to each other, I think there are some ideas that kind of bridge. And for me, one of the big ones is just recognizing patterns. It's one of the things that really defines a mathematician. And it's also one of the things that truly defines a scientist. When you just start to notice something. Like, I mean, imagine that you're Galileo and you're just staring up at the stars and you notice something because you see a pattern. Or you're Archimedes. Or you're any one of our number of famous mathematicians in history where you're just sitting there going, hey, when I look at the circumference of a circle compared to its diameter, I notice a pattern. It's those kinds of things, that way of thinking that really bridges mathematicians and scientists. So think about that pattern recognition in this next activity. All right, so I think probably one of the toughest jobs in Marin is being a developer, a land developer. But let's pretend for a moment that I'm a condo builder in Marin. I know, boo! And I'm going to develop open space. Start throwing tomatoes and bagels at me. All right, so I'm a condo developer. And I want to build a condo. And my first condo looks like that. It's just one wing pool. Beautiful, isn't it?
Beautiful. Nice development.
It looked good in a green patch of grass.
Where's the parking?
But yeah, where's the parking and how is it sustainable?
Affordable.
And affordable. Yeah. So, you know, what happens when we give developers a little bit of space? What do?
Take a look.
Blow it up.
They want more. I want something bigger and better. So it's not enough for me to just build my one little first iteration condo. I come back to my city council and I say, you know what? I want to expand on this guy here. As a matter of fact, I want to start building some wings off to the sides. And if I go that way, then I also kind of want to go the other way. And I'm not done yet. I want to go up. And so my next iteration condo looks like this guy here. So off of each of my original walls, I go one in each direction, and then up the middle, I go up one more. And so I've got these little everlasting gobstopper condominiums. That's kind of interesting. So I want to throw out kind of a math, science, I see some patterns question to you. And that question is, when you look at that, what questions could we ask?
At what rate are you increasing the square footage of your place?
Okay, at what rate am I increasing? In other words, what's the change in the in the volume of the design? Okay, so,
Square foot.
or in other words, how many of my Langer cubes does it take to build that next one? So the first one took 1, the second one took
No, 6.
6. That's interesting. Well, okay, so now, what do you wonder? Maybe a kid might wonder, I wonder if it's going to take 5 more to build the next one. Or I wonder how many it's going to take to build the next one. So, of course, because I'm a greedy condo developer, I'm not done yet. I'm going to take my condo, and again, I'm going to expand 1 block off of each side, and anything that was there before, I'm going to start building up. Up, up, up. Just go up again. Everything goes up, because that's how I am a developer. And so my new guy looks like this.
Oh, okay.
So again, I'm going to ask you my 2 questions. What do you see? What patterns do you like?
It's all
So there's some symmetry to it. There's also some 3-2-1 patterns. There's a lot of ways to look at this. Okay, so I'm not done yet because not only am I a developer, I'm also a mathematician. The challenge that I have for you, I'm going to give you two challenges. Let's give these guys some names. My first iteration condo, remember, was just that block. My second iteration combo, I don't even know where I put it, was 2 up and 1 over in each direction. So I'm going to call this a 1 con. I'm going to call this my 2 con. My 2 con is 2 high in the middle and stair steps down in each corridor. Okay? I'm going to call this guy here my 3 con. Because it's the middle tower is 3 high and it stair steps down on each of the corridors off to the side. So my question for you is, if the developer wanted to make a 10 con, how many linker cubes would it take? My second question to you is, can you come up with a pattern that lets you know any condo size and any con? Okay, so figure out how many it will take for a 10 con and figure out how many it will take for an any con. But before you start, think about patterns. That's the big thing. Think about those patterns. What do you see? What do you wonder? How can you justify it? Okay? 10 con, any questions? Go.
right, so I've got one great volunteer. I've got the second one. We have a third. Okay, a third and a fourth. Okay, great. And I'm gonna ask you to remind me of their names when they come up. So we'll start with John.
Hey, John.
Yay!
Great job.
So thank you, John, your attention.
We were people who started by drawing a picture of it, right? And then what we did was we decided that we wanted to see this numerically, and it ended up looking like a little stair step thing like this. Because the first layer had 1, then the second layer had 5, and then we were trying to see if there was a pattern for this increase here. And so then the next thing that happened was we put down the number of layers and the number of blocks. And we're looking for some kind of a mathematical relationship. So somebody in our group actually discovered that there was a mathematical relationship. It was 1 times 1, 2 times 3, 3 times 5. And so the second factor was increasing by 2 each time. And so then it was like, how is this expressed mathematically? So we figured we always started with the number of layers, which is the first number here. And then we multiplied it by the number of layers plus the number of layers minus 1. And so it was really, what was frustrating was we could see this pattern here. And but we weren't able to get any information from this by itself.
Yeah.
But once we saw this, for some reason it helped us to make the jump to this piece here. And then once we had this piece, it was just, well, how do I express that as a formula? And so again, it's right here, it's the number of layers, the first number, multiplied by the number of layers plus the number of layers minus 1. And so 4 is the number of layers here, times 4 plus 4 minus 1, which is 3. And then this number of layers here is 8 layers times 8 plus 8 minus 1, which is 8 plus 7. Or 8 minus, which is 15. Does that make sense? Yeah. But it was really frustrating getting from this to this and getting from this to this.
Can I ask a question, John?
Yes.
Who in your group found found the multiplication relationship.
This right here,
Well,
Yeah.
after you just showed how to do that input-output chart,
which
so I
is
did that,
this
and
thing
then,
here.
because I'm always like, it's the end, it's the result, how do I get the result? That's how I got it, so then I started looking at the relationship
Relationship
between
between the
2
three
and 6, 3 and 15.
Was there one particular product that jumped at you first?
The 3 and
The 3 to the 15?
15. Yes, the 15. And then I looked back at the 3 and I was like, well, wait a second, 3 times 5 is 15. Maybe there's.
So this is just kind of a pedagogical aside, but think about, when kids start to learn the multiplication tables, so third grade teachers and fourth grade teachers really think about this. When we have our kids drill and drill and drill and drill, that's only part of it. The other part of it is being able to think in the opposite direction. I've got 28. What two numbers might I multiply together to get me 28? And it's that kind of thinking that led you to that pattern. That you had this, not just ability to multiply it, but a sense of multiplication. And that tool allowed you to mathematically see a pattern that you wouldn't have otherwise seen had you not had facility with your facts. But those facts became your tool for modeling.
Okay, I want to, the other piece of that that's important as well is that we know, and we all did it when we're working on a problem, that we can see some patterns this way. But in order to figure out what the function or the formula is, we have to see what's happening this way. And what she's describing is looking at, oh wait, what am I multiplying 2 by to get to 6? What am I multiplying 3 by to get to 15? And looking at that relationship is such an important one. And that's a hard one for kids to get. Because we can, and adults, thank you. It's a hard one for everyone to get. Because we can see a lot of patterns this way, but we also need to see what's happening across the input and the output. Okay, thank you, John. Okay, I had a second grade volunteer, I believe it was, to remind us of your name. Adam? Adam, come on up.
So this kind of blown up because Jessica almost immediately at our table started diagramming this in a way that sorted it out, but we never got to the formula part. But she started diagramming the towers like this. Adjusting, yeah.